Hello and welcome to part 3 of C Programming 0 to Neural Networks, where we learn C programming from scratch all the way up until neural networks. On this video, on this part, we're going to do a visual intro, so let's get straight to it. Scene switch. So this is an example of a very simple neural network. That's what they look like. This is how I shall describe this picture so you understand what you are seeing. So if we divide this picture up into 3 columns, we'll call them layers. So in the leftmost column we have 2 circles, and then the middle column we have 2 circles, and in the rightmost column we have 1 circle, one big circle, and all the circles in the left hand column connect to all the circles in the middle column, and all the circles in the middle column connect to all the circles in the right hand column. If we consider our leftmost column to be our inputs, and our rightmost column to be our outputs, and our middle column to be our hidden layer, shall we call it. And this is how we describe a neural network. This is kind of what they look like, and this is the kind of thing we're going to be learning to program here in this series. That's a very simple neural network, this one. It is, I mean, we can't learn very much with that simplicity. We haven't got enough complexity. We can use it to learn some things, and it's certainly a useful fragment of a network, a little bit. But we can make more interesting networks than that. We need to learn how to program these and learn what those lines, what the circles mean, and what the lines between them means. And it's not as complicated as you might think. Now, there's a bit of maths involved, but it's not as complicated as you might think. Let's play around with this network, shall we? So let's make that middle layer. So this is the bit of the program that specifies how many circles we have in each layer. And if we put a 12 in our middle column and remake the program, things have got a lot more complicated very quickly by just having a 12 in that middle layer. So now we have 2 inputs going into 12 neurons going into 1 output neuron. Interesting stuff. So what we need is to build neural networks which we can pretty much use any arrangement of architecture, of network architecture we want, and play around them and see what results we can get. We can build more complicated networks than that. We can have another layer of 12. And then let's see how complicated things get now. Look at all them connecting lines. There's a lot of them. Suddenly, by just having 2 layers of 12 rather than 2, this is starting to look like a very interesting thing. And wouldn't it be interesting to be able to program that? And that's the point of this introduction. Let's all get excited about learning neural networks and get well into them, because they are fascinating things. Let's put a layer between them 2 of 24 and see what we get now. Look at that. Look at that complexity. So without any foundation in neural networks, it's going to be hard to describe what's going on here and how we end up from inputs to outputs. But we're going to find that out in this series. This visualization program I've knocked up for this video specifically. But when we get past the C fundamentals, we're going to go straight onto graphics programming, because graphics programming is a great way to learn how to apply your fundamentals. And we're going to basically build a network visualization application. In fact, we're going to go further than that. I added some zoom functionality on it, and I also made it possible to move around the network. We're going to build a sort of command center for neural networks in graphics programming, where we can have lots of different ways of visualizing our neural networks to see its activity as it's doing its magical work. And this is how we're going to learn neural networks. This is how we're going to learn to understand them. Zoom in as well. Look at all this complexity. Interesting stuff, eh? I did make a really good one before, and I used it for my thumbnail. 2, 6, 12, 24, 12, 1, 12, 24, 12, 6, 2. Now, this is a bit of a ridiculous network, but I thought it looked a bit like a human brain in this kind of strange kind of way, because you've got 2 hemispheres to your brain and sort of a central connecting thing between the 2 hemispheres. And I thought the inputs on the left and the right, at the top and the bottom, they could be like audio and visual inputs going into two networks which arrive at a single central thing. And then that could connect to something else. Interesting, eh? It looks good though, doesn't it? Now, it doesn't render very clearly when I'm recording this on video because I am I'm running my laptop output through a capture card into another computer to record, and we lose a lot of the when I look at it on the recorded screen, it doesn't look very clear. But on my computer, these lines and all the colours are precise and accurate, and it looks incredible. I think so anyway. I think so. I'm well into a bit of graphics programming every now and again. I'm not massively into 3D programming. I can do bits, but it's not really my my field. I just know what I need to know to do the things I like doing. But I'd still love graphics programming. I love making things appear on the screen that look interesting, and this looks interesting, doesn't it? So we're gonna basically, once we've got past C fundamentals, we're gonna make this. We're gonna work our way through graphics programming up until we can build a command center, a visual command center for our neural networks. Command center is probably the wrong terminology. We'll come up with a better terminology than that in time when we've figured out what it is. Right, anyway, let's get on with the third part of our series of C to neural networks. So we're not actually going to be doing any programming. In the last video, there was something I was going to tag on to the end of the video, and we didn't have time. We got to 40 minutes, which was far too long. But I didn't want to skip it because it's kind of important stuff. It's important stuff. So we're going to be spending a lot of time in Paint. So if you're just waiting for the more applied, if you're more interested in the applied programming bit, then yeah, I mean, this is really important foundational stuff. I would highly recommend you watch it. There's going to be no programming. But once we've got this bit of theory out of the way, we're going to move on to lots of applied. It'll be a while before we jump back into doing Paint and drawing out diagrams. So let's do this first part. What we're going to need is to draw out the schematic of a computer. We want to revisit. On our first video, we talked about the onion layer model, and in the middlest layer, the center layer, we have the hardware. So we're going to just quickly sketch that out. So we have CPU. I'll label these. Some memory, some block storage, and then we'll do some small things. These kind of represent our ports. We'll make them all different shapes because there's all different kinds of ports, and that'll be enough for rectangles. In fact, so this definitely looks like a CPU. Let's draw some pins on it. I think this is the pretty standard way we draw a diagram of a CPU. We do a square and we put some pins on it. Right, let's switch colours. We'll label these up. CPU, memory, call this block, storage, and we'll just call this ports. We'll label a few of them. We'll make this USB 1, USB 2. We'll make this our HDMI. Shall we make this our speaker port? We've got all different kinds of ports, haven't we? I switch back to green for a second, and we have wires on a motherboard connecting all these sort of things up to the CPU, don't we? So we'll make these sort of squiggly lines represent the wires. Right, so this is the architecture of a modern computer, and we can thank the architecture of this by this chap here. It's called von Neumann, John von Neumann, who I believe is Hungarian, or was Hungarian, because I assume he's no longer with us. Yeah, died. Well, he was born in 1903. Died in 1957, quite young. He was only in his 50s. He was a Hungarian-American mathematician, physicist, computer scientist, engineer, and polymath. Now that is a good repertoire of skills to have, isn't it? That's what we want our Wikipedia page to say about all of us, don't we? So thanks to this guy, the main thing we sort of get from him is that we have a CPU, a processing unit, and then we have memory over here, and we move stuff into the CPU from memory and move stuff out of the CPU back into memory again. We take that kind of architecture for modern computers, and if you're using a phone or a computer or whatever to watch this on, that's the architecture you have in your device of any kind. This isn't the only way to do electronic computing, but it turns out to be the best for the kind of systems we build and use. So what we want to do, our neural networks, our first generation of neural networks are going to be running on this guy here, the CPU. So the big ChatGPT-4s and those kinds of things, they run on massive banks of graphics cards, basically GPUs, which do vector multiplication and all those kind of things really quickly. They're designed to do that for games. They also work really well for neural networks, as it has turned out. But we're not going to head straight for doing those kinds of GPUs architectures, because there's quite a lot to learn to get there. So in our series, our first generation of networks we're going to make are CPU networks. So we need to have a bit of a better understanding of what a CPU is, because that's where our networks are going to run. We will then do a second generation network, and then maybe a third generation network. We'll see. We'll see how far we get with this series. For now, we'll just think that we're running our neural networks on a CPU. So what's a CPU? Let's go back to green again. Let's do our big CPU. I won't bother putting the pins on this time. This represents a CPU, and we want to a different color. We're even going to label it because we haven't put the pins on. So we're going to label it and underline it, CPU. So what's a CPU made out of? It's made out of certain key components. So we have registers. We have an ALU, which stands for, if I can fit it in, Arithmetic Logic Unit. An arithmetic logic unit. We have a clock, so the CPU can tell the time. I'm joking. We have a clock. We have buses, and we have a control unit, and we have cache. So they're your key components of your CPU. That's what your CPU is made out of. So a brief overview: registers are memory locations that are closest to all the circuitry of the CPU. They are small memory locations that hold values of certain sizes. An arithmetic logic unit is the part that does maths and logic. So if we're taking two numbers, timesing them together, the bit that times them together is in the arithmetic logic unit. We have a clock which ticks, so we do one operation at a time with every clock tick with our CPU. We have buses which transfer data around the computer and in and around the CPU. We have a control unit which controls which operation the CPU is doing next, and we have cache, which is additional really fast memory inside the CPU where we can buffer up lots of things that we're about to compute, so we don't have to continually fetch things from memory. That all sounds a bit complicated, doesn't it? Let's jump to let's call it CPU.txt. So let's describe our CPU calculating 6 times 2. 6 times 2. So what? Now, CPUs are a bit more complicated than this. I'm doing a very basic explanation here. The reason they're a lot more complicated is because we have things like superscalar processors now. And that would be quite a lengthy conversation to have. And we'll likely have that conversation further down the line. But not until we know how to build neural networks and we're at a point where we want to optimize them to run on our hardware. And this is why this is why we're getting this low in our introductory to this series, is that we're going to be revisiting these things eventually. So let's talk through a simplified version of what happens when we do 6 times 2 with our CPU. So clock, so we're doing capitals, clock tick 1. We'll do a semicolon. Our control unit fetches the first value 6 from memory and stores it in register A. That's the first thing that happens. And then clock tick 2 control unit fetches second, that shouldn't be capital, second value 2 from memory and stores it in register B. Clock tick 3 control unit instructs ALU, arithmetic logic unit, to perform multiplication on values stored in register A and B and store the result in register C. Then control unit transfers, shall we say, value in register C into main memory. So that's kind of what happens. So doing this like this kind of illustrates how these components sort of work together. So we have a clock tick where sort of one thing happens every clock tick and each thing is isolated from the previous thing and the next thing. We have a control unit which sort of moves things around and decides what's going to be happening next. And we have an arithmetic logic unit which can perform operations on values. So our CPU will say fetch the value 6 from memory, from RAM, put it into a register, fetch the value 2, put it into a register, perform a multiplication and store the result in another register, and then transfer that register's value, which is the result, back to memory. So that's kind of the architecture that we're working with. That's kind of how a CPU works. It's only a rough sketch of what's happening, but it does give you a sense of how all this goes together. The other two things we haven't mentioned are buses and cache. So buses, it seems like an unusual name, isn't it? A bus. If you think of a real bus that you sort of get on and take a ride on and get off at a different location. If we called a bus a people bus, it's a people bus because it buses people around. It transports people from one location to another. Well, in a CPU, in a computer, we have a data bus, an address bus, and a control bus. The data bus buses data around our system from one location to another. The address bus buses addresses around from one location to the other, another. And a control bus buses signals around and from one location to another. But really, it's a very appropriate name. It's a transport mechanism for moving things around inside our computer and inside our CPU. Cache is really fast memory. We will need to go into cache later on when we talk about optimizing our neural networks, because with working in C programming language, we can target our neural network to run on a Raspberry Pi if we want, and we can make it so it runs optimally well on a Raspberry Pi. Or we can target our neural network and compile our neural network to run on a £100 million supercomputer. and we can take that same neural network and deploy it on a massive hardware optimized for that hardware. That's one of the many great things about working in the C programming language. We're right where we need to be. We have a one-to-one relationship with the hardware and what's going on inside the computer, and we can specify all kinds of important things for different hardware and different architectures. So what we want to do, we're going to be doing our calculations for our neural network are going to happen in here in the ALU, the arithmetic logic unit. So what we want to understand is, what is an arithmetic logic unit? How do you make an arithmetic logic unit? How do you make a processor? And it's going to give us some insight into raw computer science. We're not going to be revisiting electronic engineering again in this series because we don't need to. We might reference it a few times, but electronic engineering, well, computational electronic engineering, and programming. The lower you get with your programming, the more you sort of cross over into a world of electronic engineering. It's not like there's two different worlds. There's sort of a seamless transition between the two. So it's worth knowing this kind of stuff. It's definitely worth knowing this kind of stuff. And as I said, after we've got through this final theory-heavy part, we're going to move on to practical kind of programming. But let's go through it anyway, because it's going to give us a sense of how amazing computers are. So what are computers? What is a CPU made out of? You might think silicon. You might think wires. Well, the one word that a computer is made up out of is transistors. Transistors are what we make computers out of. Transistors are what make electronic computing possible. I think it's a MOSFET transistor. MOSFET transistor. This is what we make our computers out of. Metal oxide semiconductor field effect transistor. That's what we use. And a little bit of information for you. A MOSFET transistor is the most manufactured product humans have ever made. We've made more transistors than we've made anything. That's interesting, isn't it? Well, it is kind of does kind of make sense, as one CPU can have billions of transistors. So, yeah. So what's a transistor? If you drew a electrical diagram, a transistor looks something like this. That's kind of how we draw it. We're not going to use the standard drawing. We're going to just make our own, because we're not electronics engineers. We're programmers. We are C programmers in the C programming language. So we're going to have 3 pins. There are 3 parts to a transistor, and we may as well join them up so we can see it's one thing. And we're going to connect. That is a symbol for a battery. Don't worry if you don't know electronics engineering. Again, we're not going to be coming back to this subject. It is a bit of an overview. We don't need to know this to be pro C programmers. And then we're going to call that out. And we're going to have an in there. And we're going to point that to there. So we need to label these different parts of our transistor. So we're going to call this the base. We're going to call this the collector. I'm going to call this the emitter. Base, collector, emitter. Now let's say we've got a continuous voltage of 4.5 volts going down there. And let's say we put a 1.5 volts into here. So our transistor will be configured or manufactured to operate within a certain range. Let's call 1.5 volts our low voltage and make that equal to 0. Let's call 4 volts our 4.5 volts our high voltage and make that equal to 1. So our transistor works is, if we apply the low voltage to the base of, say, 1.5 volts we've specified here, then no current can get between the collector and the emitter. So our output will have 0 volts. If we apply a high voltage, 4.5 volts, to our base, and current will be allowed to flow through the collector and the emitter, and our output will be 4.5 volts high. Now, let's redraw this diagram a little bit. Let's get rid of these 4.5 volts and 1.5 volts. We're just going to use zeros and ones to represent the lows and highs. So we've got 1 there, and if we apply a 1 there, we get a 1 there. Make sense? If we apply a 0 there, we get a 0 out. Does that make sense? Shall we run through it again? If we apply a low voltage to our base, no current flows between the collector and the emitter. If we apply a high voltage, current flows. Current is allowed to flow through the collector and the emitter. So as long as there's current flowing into the collector, there'll be current flowing out the emitter. And we've arbitrarily labelled this is the out and this is the in. We can even draw a table in, out, to represent this. I should have really separated this from that. And we can say if in is 0, out is 0. If in is 1, out is 1. Not a very complex architecture. So how do we build computers out of the ability to do that, out of having electronic switches? Well, let's find out. What we need is more transistors. So, let's do a transistor up here. In fact, that's probably not quite far enough over. Let's do a transistor here. And we're going to make it these strange little triangles again, just to show we're working with one thing. And we'll do another one here. There's another transistor, and then we're going to do one more. So we've gone from one transistor, which can, if the input's 0, the output is 0. If the input's 1, the output's 1. So we need ins again. So at this time we're going to need two inputs. So we're going to have input 1 going into the base of that transistor. We're going to have input 2 going into the base of the second transistor. We're going to have a continuous current going into the collector. I'm going to call it 1. I'm going to do the same thing in this one. A continuous current going into, make sure that arrows, and we're going to give that a 1, a high. Shall we label these up here again? We'll just put 1 equals high, 0 equals low. We can also say true and false, because this is a binary, so we can kind of imagine it representing anything which is a sort of binary. And a true and a false is a binary, isn't it? So what we're going to do is we're going to connect the CE and then we're going to do the same thing here, BCE. We're going to connect the output, the emitter of this transistor, into the base of this transistor. I'm going to connect the emitter of this transistor into the base of this transistor, and then we're going to make this our out. So let's make sure we can see the important parts. In, into, out. So we have this arrangement of transistors, and we want to, just like before, draw a little table and see if we can see what's going on. So let's do our table down here. And we've got in, 1, in, 2, and out. We seem a long way off being able to do neural networks, don't we? And do calculations. You can consider this information to be supplementary. It is important and it does matter, but it's not probably going to make you a better C programmer. It is going to maybe illuminate a few things about computers that you perhaps didn't know. So let's go for another colour to do our one. So we don't want to do red. Shall we go for blue? So let's start with 0. Input 1 is 0. Input 2 is 0. So there's a 0 there and a 0 there. What's going to be our output? Well, let's do input 1 first. Input 1 is 0 to this base, so no current is going to go through the collector and the emitter. So that means this is going to be 0, which means this is going to be 0, which means no current is going to get through here, which means the output is definitely going to be 0. We don't even have to look at input 2 because we know the output is 0. Let's get rid of these. We know 0 and 0, the output is 0. So what about 1 and 0? 1 and 0. What's going to be our output? Well, this time our input 1 is applying a high, a 1, to this base, which means this current is going to flow through the collector and the emitter, and then that means this is going to be a 1, so this transistor is going to be, shall we say, activated and allow current to flow through it. So we need to figure out if there's any current flowing into it. Well, this is a 0, which means this current isn't getting through this transistor, so that means this is a 0. So there's nothing going into the transistor, so the output is going to be 0. 0. What about the other way around? This is obviously the simplest and, may I say, scruffiest example of going through this. There are some fantastic resources on the internet that will explain this in much more detail. I'm just using a paint program. There are better tools to explain where we're going with this. But as an introduction, in this series we're interested in programming neural networks. So we don't need to be electronics engineers, but we do need to have a little bit of an understanding of what's going on inside our computers. Hence this video, hence this part. So this time input 1 is 0 and input 2 is 1. What's going to be our output? Well, we've already been here before, haven't we? If input 1 is 0, there's nothing flowing to this base. So even if input 1 was 1, which it is, because current's flowing through it, it's not going to make it through this transistor. The output is going to be 0. And then the final case, obviously, and I think you can probably guess where this is going now. If that's a 1, then current's flowing through this transistor, so that's a 1. And then this transistor is activated, it's going to allow current through it, and there's current going into it, so the output is 1. That should be 0, that should be 1. There we go. So input 1, 0, input 2, 0, output 0. Input, yeah, well, I won't read it out. But here we have a representation of this connection of transistors. And we call this diagram here, we call it a truth table, which kind of explains why I said these could represent trues and falses. Because if we read it as true and false, input 1 is false, input 2 is false, the output is false. Input 1 is true, input 2 is false, the output is false. The only condition where the output is true is when input 1 and input 2 are true. That's the only condition that meets that makes the output true. This, we call it an AND. And we don't just call it an AND, we call it an AND gate when we're talking about transistors. It's a logical AND, which you'll use in language and you'll use in all kinds of things. You could say, I'm going to go to the shop if I'm hungry and it's not raining. It's a complex logical statement. I threw a not in there. But we can see both conditions need to be true for the output of going to the shop to be true. It makes as much sense in language as it does in computing terms, because we're dealing with primordial logic, first order logic. It's called first order logic. So out of a series of 3 transistors, we can represent a logical AND in an electronic currents, admittedly, but a logical AND. We've got more of these. I'm not going to draw this whole diagram out again, because this is not the best way to explain it, as I've sort of stated. This is kind of a scruffy overview. So we have a logical, let's go back to yellow because it's the most visible on a black screen. We have a logical AND. And this we can represent with a sort of symbol. It looks a little bit like a bullet, strangely enough, but AND written in that. There's other things. There's other arrangements of transistors we can do to represent other types of logic. So we have this one, which doesn't look that dissimilar, apart from you do that. And this is called an OR So what's a logical OR? Well, let's draw out a table and find out. That's a terrible table. Let's take your time, do it a bit slower. In 1. So once again, we've got two inputs. Input 1, input 2, and output. In 1, in 2, and out. So with input 1, so we'll do the same, all the combinations we can do. There are all the different combinations we can have of our inputs. That's an exhaustive list of the different combinations we can do. With an OR, unlike an AND, when either input 1 or input 2 are true or 1, the output is true or 1. So that would be 0, but that would be a 1, that would be a 1, and that would be a 1 because we still satisfy the condition that input 1 or input 2 is true. We actually call this an inclusive OR. An inclusive OR because it includes this condition. And that means that we obviously have a different kind of OR. We have an XOR. And the only way that differs from our inclusive OR is, in this case, our output is false. So exclusively input 1 or exclusively input 2 need to be true or 1 for the output to be 1. But if both of them are true, the output is 0. And there are more, and there are even more. I shan't draw out the truth tables for all of them. We're just getting an overview. We have a NAND, so we have a not AND, which is an AND but inverted. We have a NOR, which is an OR inverted. We have a NOT. We have a NOT, which is an inverter. We have a variety of these. Now, it's hard to imagine how we go from logic gates to building a computer that can hold values in memory and move data around and perform calculations. Well, we carry on with this exercise that we've just done. So we went from having the simplest building block of a transistor, and then we can arrange transistors into complex patterns to represent logic gates. And once we've got logic gates, we can do the same thing again. So we can take our logic gates and OR, NAND. I'm not actually drawing out an actual example here, I'm just explaining the principle, so this isn't going to make any sense at all. How do you do a NAND? You just put a thing, no you don't, you do a circle at the end of it, don't you? That has 2 inputs, that has 2 inputs, that has 2 inputs. Well, we can wire these up in all kinds of crazy ways, can't we? That wouldn't make any sense, but you know. We can put that in there, I don't know. We can wire all these up into unusual patterns and build even more complicated things and represent more complex logic. For example, we can represent a D, flip, flop, and an SR latch, a set, reset latch, and a 4-bit adder. Now we're not going to draw any diagrams out for these or even explain what they are. They are just examples of complex logic that we can build out of first order logic. So we can take simple building blocks like ORs and NOTs and ANDs and NANDs and NOTs. I think I said NOT twice. And make complicated patterns like putting together a Lego set and make these even more complicated patterns, which we can wire these up together, and we end up with ever increasing layers of abstraction away from starting with a simple transistor. And that's how we build a computer. And that's all I really wanted to get to in this video today, was a brief introduction of this. I would highly recommend having a bit of a search around on the internet and finding more of an electronics engineering explanation of this. But the reason I wanted to tag this on the end of the last video is that we discovered that computers count in binary. We never really addressed the question of why computers count in binary. They count in binary because they're made out of transistors, and transistors are electronic switches that can have 2 states, 0 and 1, low or high, true or false. And out of transistors we build logic gates. And out of logic gates we build complex logic, and out of complex logic we build computing devices. And that's the story of computers. But it does bring an interesting perspective. So if we go back to our We don't need to, we'll save it, we don't need to save that, do we? If we go back to our visualization. So, we don't know enough about computers yet in this series to really give a good explanation of what's going on here in this network. This is a terrible example of a network because it is it's network art. Let's go back to the really simple example we started with. 2 inputs, 1 hidden layer, 1 output. This is an example of a feed-forward network. The connections represent weights and biases which are applied to the next layer, to the activations in the next layer. And our network arrives at a result by adjusting its calculation, adjusting its weights and biases. And what are these? Are these just programming? Are these circuits? They're actually electricity, aren't they? I've got rid of everything. If our computer is made out of transistors, which is controlling the flow of electricity through circuits, then our neural networks are operating on electricity. They could be thought of as an electrical phenomenon. I like to think of it like this. Let's do a good outro to this video. So we sometimes think of human progress as in terms of industrial revolutions, don't we? Or at least that's the economic perspective. We have the Industrial Revolution of the 19th century, where we built steam engines and those kinds of things. And then we had previous revolutions to that. Not really revolutions, but economic epochs. I prefer not to think in terms of economic epochs. I think in terms of humanity's ability to harness and gain control of fundamental forces. If you think of fire, the difference harnessing the power of fire made to humanity. How many people died in the winter in colder parts of the planet? Because they didn't know how to make a fire. Then we knew how to make fire. It's a trivial example, but that epoch of being able to make fire to keep warm in the winter, which I would guess is how we came about it, that led to the Bronze Age, where we were making things out of bronze. And then that led to the Iron Age, where we were making things out of iron. Admittedly, we mostly made swords and killed each other with them, but technological progress nonetheless. The age of the fire epoch took us all the way up to the 19th century, where we didn't just learn to make steam engines, we also learned to harness the power of electricity. And that epoch, the electrical epoch began. Went from the fire epoch to the electricity epoch. And that's what we're in now. And we have such command over electricity that we can build machines that perform billions, if not trillions, of calculations a second. And out of that, we can build neural networks which learn input data and be able to organize it into some kind of output, which is incredible. And it's all just electricity. Isn't that incredible? So this is a supplementary video. This is a supplementary part, but I've probably not done a particularly amazing job of enthusing people on how interesting neural networks are, but let's make another interesting pattern. We did binary last time, didn't we? We covered bits and bytes. So how did it go? We have 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s. See what a byte looks like as a neural network. You'll notice a bug in my program. So the final layer doesn't render properly, does it? And if I zoom out, it shifts. And if I zoom out again, it shifts again. Then it looks kind of all right, and then it shifts again. What an unusual little bug in my program. I did make this in about 20 minutes. But I thought I'd have a quick hacky run through, because then I need to work my way back and then make the whole graphics program thing into a good explanation when the time comes. But isn't that an unusual little bug? It sort of bobs up and down. It's a very strange phenomenon. And that it starts to affect other layers as you zoom out until you go really small. I limited on the zoom small, because it eventually divides by 0 and crashes the program if you don't. And then if I zoom in too much, then it slows down to a point where it just crashes. because I'm not clipping the rendering. I'm rendering this massive thing, and then it's only a certain amount of it is actually within the bounds of the screen. So this is a very hacky program. But pretty soon, following this series, you're going to be able to make programs like this, even just network visualizations. I mean, look at that. It's like artwork, isn't it? It's incredible. And that's just made out of our ability to harness the power of electricity. I've become very interested in neural networks in recent times. In about the last 18 months, I followed the progress of neural networks, of artificial intelligence my whole life, since I was a kid. And the thing about artificial intelligence is a lot of it is like a bit like a magic trick. If you know how the magic trick works, then it doesn't quite seem so magical, does it? And it's only in the last few years, maybe the last 10 years, that we've really started getting the kind of results we were always hoping for. Now, neural networks aren't thinking machines. Neural networks aren't Lieutenant Commander Data from Star Trek, and they're not C-3PO from Star Wars. They're not consciousness. They don't have any awareness, and they're not really thinking. They're just adjusting parameters. But for the first time ever, we have opened a window or a crack into this sphere, this realm of understanding that we knew nothing about before, which is what is the nature of intelligence. An exploration into neural networks is an exploration into the nature of intelligence and identity and consciousness and all those sorts of things. It's fascinating. This might not be the answer to Lieutenant Commander Data and making evolving, learning androids that we can have personal relationships with, but I guarantee it's part of the solution. I guarantee it's a part of it. It allows us to have our computers work with inexact data and make inferences and make almost judgments on that data. And with more parameters and more computing power, we can do that with huge data sets. We can massively outpace human accuracy on certain things now. Identifying images. We've got to a level where computers are better at that than humans. That's a really difficult thing to program. They're still not perfect. And we're only at the infancy with this kind of technology. We're only at the very beginning of figuring out where to go with all this. And this is why this is the best thing to learn in computers right now, and why I'm doing this series, because I'm not somebody who's got 20 years industry experience in neural networks. I'm a computer guy. I absolutely love computers, and over the past 18 months I've been learning to program neural networks and playing with them and messing around with them, and I've opened up avenue after avenue after avenue of interesting things to do with neural networks and interesting directions to go in. And it's very much a trial and error, new frontier computer science. This is the place you want to be working in and learning about. This is the interesting realm. This is, again, it's probably not the answer, but I guarantee it's part of it, or at least it's a step towards it. And whatever it is we're trying to get to, I would imagine we're trying to get to. I like to think realistically of where we're going to get in sort of my lifetime and reasonable human lifetimes of people who are alive today. We're not going to be in like Star Trek universe where we're beaming up to planets and jetting around the galaxy in a warp ship. And we're not going to be like Star Wars where we've got lightsabers and that kind of thing. It's not realistic. We're not going to see those kind of things, even if they are possible. They're obviously just sci-fi things, but there are some things in sci-fi that have come to pass, and I think one of these things will be in our lifetime, like, shall we call them droids from Star Wars? Droids that you can have a relationship with, that learn and evolve and can communicate with humans in natural, normal ways. There's loads of research in those kinds of fields. And there's loads of sort of test products and prototypes that you see, and none of them are very good. None of them are very good, and they all need massive amounts of computer power to not be very good. But I would say in our lifetimes, we're going to be able to build those kinds of things. And there's loads of little little niche areas where we can apply a bit of neural network magic and make really magical things. So without even thinking about the big, trying to make droids, we're just making our computers come alive a little bit more and have be able to be more assistive with us. We can do that with little bits of neural networks that we don't need supercomputers to run on that. We can just run our own machines. So anyway, this is a bit of a big outro because we're going to go into some pretty much applied programming from now on. So I just thought I would make an attempt to kind of illustrate why we're doing this series, why I'm doing this series, and why people should follow it, why you should follow it. And it's going to be fascinating. It's going to be interesting, and it's a good challenge for me because I'm explaining it all the way up from the beginning, and I've been programming for a very long time. So. And I do like a challenge, and I also like explaining things. So if you would like to learn this kind of stuff, stick with us. I will get you there. You will know everything about neural networks, up to the amount I know about neural networks, which isn't a massive amount, but I'm actually quite far ahead I'm a lot far ahead of where we are in this series at the moment, and I will continue learning. So by the time we get up to what I know, I've already learnt a load more stuff, and we'll be making fascinating things. Right, I will call it a day at that. That is our part 3 of neural networks. So prepare yourself for part 4, where we're going to be doing applied programming, and we're going to continue with applied programming and learn all the C fundamentals. So there'll be a lot less theory and a lot more programming. Right, all the best. See you next time.